notes here. So remember this example here. So that's the formula for the Poisson distribution that we use when we for our earthquake engineering seismology problems. So, and usually the typical formula is, so that's the number of occurrences, right? Number of occurrences. Okay. Given this distribution, it's usually like the form of the equation, the form of the is this. Is the mean. Okay, so in our situation for earthquake or seismology, that's our mean. Okay, that's the annual exceedance probability multiplied by the design life, or the amount of time that we're interested in. Okay, and the rate of projected ground motion design life of the structure. So, if we want to calculate the return period for an event that has 10% probability of occurrence in the design life of 50 years, okay, so we want to find out what this is, the annual exceedance probability, right? So we'll find out what that is. So, years, okay. And probability equals 10%. Okay, so we need to, this is based on probability of at least one successful outcome. Just take that for now, okay? When we calculate this as one successful outcome, and when I give you the problems, I'll actually state that out clearly. if you say, when you have the probability of at least one successful outcome, what you need to do, we need to adjust this formula, right? This formula here. So the probability, so we have to find out, so basically what we need to find out is the probability that there's greater than 0 occurrences of this, right? And for the probability to be greater than 0, it means 1 minus the probability of the event not occurring. So that means we have to do this derivation, okay? So, which you can see here. So the probability of at least one event, okay, is 1 minus the probability of no events occurring. The probability of no events occurring is that. So how do we get that probability of no events occurring? Is, if I put it into here, no events occurring is 0 to the power of 0 equal to 0 there. So anything to the power of 0 becomes 1, right? And 0 factorial is 1. So that equals this. Okay. And then, so then that formula there, probability of at least one successful outcome, the equation then becomes this. X greater than 0, so at least one outcome equals 1 minus the probability of 0 outcomes. And that equals 1 minus, okay? Okay, so now we use this formula here with the information we've got. Okay, so then if I want to, so then basically I say, using this formula here, I can say 0.1 equals 1 minus e to the minus lambda t. Okay, my t is 50 years. Okay, and then I can go back and solve for lambda. Okay, so lambda will end up being 1 over 475. And so what's the inverse of the annual exceedance probability? It's the return period. Okay, and so that's why we inverse that and we get a return period of 475 years. Okay, so that's kind of it might take your head around. Might take you a little bit to get your head around that relationship there. But obviously, if an event occurs 3 times a year, let's say 4 times a year, then the return period is going to be the inverse of 4, or 0.25 of a year, right? It's going to come in every quarter of a year. Likewise, if it's less than 0, less than 1, then obviously your return period is going to be greater than 1, right? Inverse. Okay. So that, anyway, just note that how we got this from here, okay? With this information, and we take into account at least one successful outcome. We use this formula, we derive that formula, and we calculate that. Okay, so now let's look at some other examples. So again, going back to this homework question, right? Now, the seismicity, so here, this homework question. The seismicity of a particular region is described by the Gutenberg-Richter recurrence law as that. Okay, so Okay, so and remember we've got this, you know how to come up with this now, it's a relationship that's like that, right? Log that. Okay, so from that we get that. So now we can answer these questions in relation to what's the probability of a magnitude event, an event occurring with a certain magnitude. We can work out the annual exceedance probability, okay, and answer other questions. So let's have a look at the type of questions. What is the probability that at least one earthquake of magnitude greater than 7 will occur in a 10-year period? Okay, so my question is, which form of the equation are we going to use? Are we going to use this one? Or are we going to use this one? Bearing in mind what I said. What's the key thing? What's the key thing in this equation, in this question? What is the probability that what? What does that say? At least. So when I say at least, which one are we looking at? That one or that one? This one, right? Because this is when at least means we take up the probability of it not occurring. Okay, so we use this form of the equation. Okay, so the first thing for these type of questions I want you to just notice, and I'll put it there, okay? This one here, what is the probability that exactly one earthquake of magnitude greater than 7 will occur? Which equation are we going to use? Yeah, the top one. Okay, so this is exactly, okay, exactly whatever that value is, exactly 1, 2, 3, 4, 5. Okay, we'll use this one. This one here, if it's at least we use this one. Okay, 1 minus that. Okay, and so then all we need to do. Okay, so what is the probability of at least one earthquake of magnitude greater than 7 will occur in a 10-year period? Okay, so let's look at how that's solved using that relationship. And you've got the answers. I've uploaded the answers last week or the week before. So have a look at these when you get a chance. Okay, A. Probability that the acceleration of 0.1 g will be exceeded in a 30-year period. Okay. That's a question. Probably. No, it's not a question. Oh, sorry, we're looking at this one. Oh, no, hold on. I'll go to the next question. Okay, here. Okay, here it is. Okay, we've got that relationship, Gutenberg-Richter relationship. Probability of at least one earthquake greater than 7. A 10-year period, 50-year period, 50-year period. Okay, so in a 10-year period, remember we take the form of the equation, at least one earthquake greater than 7. We come up with this form of the equation. Okay. Okay, now so what we've got to calculate is we want to calculate this, right? We want to calculate that. Times t. So the question is, what is it? In a 10-year period greater than 7. Okay, so that's, we put our period in here, 10 years, right? T. Where does this come from? Where can I get that from? Exactly, so I can get that from this relationship here. Okay? I get that from this relationship here. So I put in, I want a magnitude 7.0 there. I can calculate that. Okay, so this is how you calculate it. Okay, remember to take when you're in log space and you want to go the inverse log, you go 10 to the power of that, okay? That will give me my, that is my Gutenberg-Richter relationship, okay? But inverse log, okay? So I get that, I'll plug that into here, okay? 10 years, and then I can calculate that probability, okay? So you have to do that in the assignment, okay? And same thing here. 50 years, okay, you just change the number of years, okay? And 250 years, change the number of years, okay? So what can you see happening here? Obviously, you notice that the longer the period of time, probability is getting larger, right? Obviously, the longer period of time, then there's more time for an event to occur. So, now, then the other, so that was this question here. What is the probability that exactly one earthquake of magnitude greater than 7 will occur in a 10-year, 50, and 250-year period? Well, in that case, if it's exactly one, you use which version of the equation? You use this one, don't you? Exactly. So the probability of exactly one earthquake greater than 7, you use that. Okay. And again, I use lambda. You can get lambda from the relationship for 7, magnitude 7. And I just use this formula here now, and then I get these probabilities. And what you'll notice is the probability should be reducing as the time increases, and it does. And so why would the probability be reducing as time increases?
There's more like being, there's more likely to be more than one.
Exactly. There's more likely to be more than one, right? So that's why probability is reduced. Okay. So that's. And now, here's another type of question which is similar to the one that I did from the notes. Determine the earthquake magnitude that will have a 10% probability of being exceeded at least once in a 50-year period. So, what I'm interested in this question here is I want to determine the magnitude of 10% probability. So I've got the probability of 10%. Okay, I've got the 10% probability. I've got the 50 years here. So I want to solve for that. So that's just a little mathematical exercise. And then you can go around and solve for what the annual exceedance probability is. Okay? So that's a couple of examples of using the Gutenberg-Richter relationship, okay, to come up with the Poisson distribution, how to solve these types of questions. And you can also have the same types of questions for the hazard curve. So remember that, again, this is exceedance probability, annual rate of exceedance for magnitude. And remember the same, you've got, again, for the seismic hazard curve, except what have you got on this axis? For the Gutenberg-Richter relationship, we've got magnitude. What have you got on the seismic hazard curve?
Acceleration.
Acceleration, peak horizontal acceleration. Exactly. So, and the acceleration, as you know, is very important for us when we're engineers. You know, we're always concerned about acceleration. So, but we can ask the same questions using the same Poisson distribution to come up with answer similar questions about probabilities relating to acceleration. Okay? So here, for example, in this, remember the illustrative example that I gave you, that we discussed, you'll end up with a seismic hazard curve. Okay, once you've plotted it with all these target accelerations. So using the PSHA seismic hazard curve analysis calculated above, calculate the probability that an acceleration of 0.1 g will be exceeded in a 30-year period. Okay, so again, so in that case, I've got a seismic hazard curve like this. Okay, and I want to calculate the probability that an acceleration of 0.1 g. So 0.1 g, I'd come up on my curve here, get my annual exceedance probability, and then will be exceeded in a 30-year period. So we want, when it's going to be exceeded, we're going to use this. Exceeded means that we're interested in all occurrences except when there's 0 occurrences. So we would use this here, and we would get our value from the seismic hazard curve, our annual rate of exceedance, and that would go in here, and come up with the answer for that. So again, the same use of the equation, except it's just using a different curve, right? Here. So probability that acceleration of 0.1 g will be exceeded in a 30-year period. So you get this value here from our seismic hazard curve, and we can answer the question. And then you can work backwards. Okay, for a 10% probability of exceedance in 50 years, what will be the expected acceleration level? So we've got 10% probability of exceedance here. So when you've got exceedance, that means you're talking about at least. Okay, so that's why we're using this form of the equation. And now we're going to solve for the annual exceedance probability. Let's work backwards. Okay, so that's how you use those formulas. In this example, the one we just did earlier, with everyone on Excel, you can end up with a seismic hazard curve like this here, and then you can answer the same types of questions. So if I look here, now using the hazard curve, determine the probability that an acceleration of 0.2 g will be exceeded at least once in a 100-year period. So what I'll do here, from the graph, I'd say 0.2 g, I'd come up here, 0.2 g, come up here, get my annual exceedance probability here, which equals this value here, and then I'd use that in this form of the equation to get this probability of 54%, 0.54. And again, using the hazard curve, determine the peak acceleration that will have a 10% probability of being exceeded at least once in a 50-year period. So this time we're working backwards, right? Working backwards, so we have this formula. 10% of the probability of being exceeded is 0.1. And we want to solve for this here. Okay? That there. And we work backwards to get that. And then from the graph, we've got our annual exceedance probability of 0.0021. So we go 0.0021. You come here, you come down, and the associated peak ground acceleration for 0.0021 is 3.4 g. Okay, so you can see how the seismic hazard curve and our Good-Richter relationship, and together with these Poisson distribution equations, we can solve these types of questions. Okay, so I think would be good for you to go home and just study in those answers that I've got in the tutorials. Right, it's very just read them, okay, and you'll understand it. And then you've got exactly the same thing in assignment 1, same type of questions that you can answer. And in the exam, you'll have exactly the same type of questions, okay? So it's not, once you get the hang of it, it's pretty straightforward. So that's basically all I want to cover today. I think I don't want to go on to a fresh topic now, it's a bit late. So next week we're going to look at site response. So that's another key, it's a very key topic, site response. So site response, we talked a little bit about it in previous lectures. So basically what we're talking about I'm going to rub this off now. Is that okay? Yeah. But it's a key topic, so please everyone turn up, because you will be questioned on it in the exam. And it's a key topic for your understanding of earthquake engineering, or engineering seismology. So what we are talking about with site response, right? We're talking about dynamic soil properties. Okay, so we're going to be talking about dynamic soil properties. And the dynamic soil properties, depending, say if you've got a site, this is what's called site response. So it's the response at a particular site. So if you've got your site here, depending on the dynamic soil properties in the layers of soil at your site, okay, you have your bedrock here, and you've got your earthquake wave that comes in here, okay, and you might have some sort of, your earthquake, your displacement your earthquake wave might be something like that, okay. As it passes through these layers of soil, depending on the dynamic soil properties, this could be either amplified, depending on these soil properties, it could be either amplified or it could be de-amplified. Well, it could be attenuated, right? So this is a key thing. So if you've got if your dynamic soil properties are of a certain values of your dynamic soil properties, this could be amplified significantly. Okay? Whatever response you get could be severely amplified. And this answers your question about, in the assignment I asked, you had a question about what the different curves are related to.
Yeah.
It's kind of related to this topic here. Okay, which I mentioned. So the dynamic soil properties are related to what we call, it's a big topic in earthquake engineering, also geotechnical earthquake engineering, site response. And that's related to the dynamic soil properties at the site and how they can possibly amplify any ground motion that we get at the bedrock, depending on the dynamic soil properties. So that's what we're going to be talking about next week.
Yeah, because one would think that you get less attenuation through more attenuation through softer soils.
Yes. We'll talk about it next week.
Yeah, you get
amplification through soft soils.
Yeah.
And so next week we'll talk about the reasons why.
Yeah.
And you'll understand that. And that's a really big topic in earthquake engineering. Okay. So that's what we're talking about next week. We'll leave it for next week. And so I think you've got everything you need for your assignment. So try to get cracking on that as soon as possible so you can ask me questions over the next couple of weeks. Okay, thank you.